reminders about things to be doing. So you have a few homework assignments coming up because you have a test next week. Okay. So next Wednesday is your exam. You have homework 6 is due on Sunday, and that kind of covers the stuff that we did at the very beginning of chapter 3. Homework 5 is what covers the naming of the compounds. And then I got off on my numbering a couple of years ago, and so there is no homework 7. So don't worry about it. Don't panic. We're going to go straight to homework 8, so I don't have to change the homework numbers for the rest of the semester. And that is going to be the stuff that we're working on today. Maybe a little bit of what we're working on Monday, but we should get through most of it today. So that's kind of what's coming up. Since the test is on Wednesday, I am moving my Thursday office hours to Tuesday. I would probably be in my office anyway, but I want you to feel like you can come in Monday or Tuesday afternoon and ask me questions. I will make sure that I am there, particularly in that sort of 2 to 4-ish time frame, if you have questions that you need help with. Okay. Any questions? Yes.
Your office hours only change for next week.
Yes and no. The following week, I made a doctor's appointment on Thursday before I had made my office hours. And so they'll change the following week as well, but then they will go back. Yeah, that's fine. Go right ahead. So yeah. Okay. So I think that covers all my announcements. All right. I wanted to start by talking a little bit about significant figures. Oh, I forgot this in the last class too. So some people were having trouble with the polyatomic ions. So this is not an assignment. It is kind of extra credit. So first, let me tell you about extra credit. You can earn up to 25 points for the entire semester. So all things added together, the most you can get is 25 points, which is 2.5% of your grade. So that means you could go from a B to an AB. You are not going to go from a C to an AB. You are not going to go from a B to an A. Okay, it's going to bump you over the borderline from one grade to the other. Okay, I really want you to do the work. But one of the things that I will have available for extra credit is that I will have like extra little help sheets. And as you do them throughout the semester, if you collect them and at the end of the semester give them to me, then you can earn extra credit on those. So what this one is, and there's actually 2 different versions. So one is color by number ions 1 and one is color by number ions 2, is you're going to, based on the charge, color the areas different colors to practice what charge things are. So some of them are your common columns like sodium and chlorine, and some of them are the polyatomic ions. So I'm going to put that over here, and you're welcome to take those. You do not need to give that to me anytime soon. You need to hold on to it until the end of the semester and give it back to me then. If you would like a place to put some of these things, because some of them are going to be things that like you cut out stuff and whatnot, I have some books that you can put them in, just glue them in or tape them in or whatever. So we'll talk more about that next week. Okay, significant figures. Most of you covered this in lab. There are a few people who don't have lab, and there are some people that it's just new and so it's confusing. So let's go over it again anyway. So this just summarizes the rules that are in chapter 1. So I told you we'd come back to the measurement stuff once we had something to measure. And what I'm going to do is, rather than just going through the rules all over again, they're written on this sheet. So I'm going to talk about some things that confuse people sometimes. So the first thing I hear people tell me is, well, Doesn't significant mean the same thing as important? Isn't that 0 an important 0? Insignificance, we're just talking about precision. Do we know that digit or do we not know that digit? So a 0 can be important and not be significant. So your basic rules are kind of at the top. We know that if we measure something, if I have a reported value, I give you on the test that this is the mass or this was the temperature. The reported numbers are the digits that are significant. So when you're in lab, everything that appears on the balance, it's going to be 4.9300. Those last two O's are significant. So your balance, your thermometer, they know the significant figures. Your calculator does not, because your calculator doesn't know what you're measuring and that kind of thing. So it's just going to spit out everything that it calculates. Okay. So measurements, we just trust that whoever gave us the number, those are the significant digits. But we have to pay attention to the zeros. Okay. So we know that if it is not a 0, that's important or is significant, right? If it is a 0 between things that are not 0, like 101, then it kind of goes along with the non-zeros. But then we have these zeros that might be at the beginning or the end. So sometimes those zeros are there to tell us, yes, we know that this is actually a 0. And sometimes they're there to tell us this is how big the number is. Okay. So we call those ones that tell us place value. All right. So the rule of thumb I like to keep in mind is that if I'm going to change the scale that I'm looking at, if I go from grams to milligrams, I'm just changing the scale. I'm not changing how much the mass is. I'm just how I report it. That should not change my significant figures. So I will commonly call these Sig Figs. Hopefully that's obvious that it's coming from significant figures. I'm a really bad speller, don't want to spell big long words. Some people call these significant digits. So every once in a while I'll put Sig Figs, but usually Sig Figs. Okay, so if I am changing scale, I'm still measuring the same thing. I'm still measuring mass. I'm just doing it in units of grams instead of kilograms. I might be doing it in ounces instead of grams. I'm changing the unit, but I'm still measuring mass. Okay, that's what I mean by changing scale. So this should not change my number of significant figures. As a rule, kind of going along with this, actually, I'll come back to that. Okay, so let's say I have 0.0518 grams of a material, but I need it in milligrams. Okay, for some reason, the next calculation I'm going to do is in milligrams, so I need this in milligrams. So using that same dimensional analysis that we did the other day, we are going to have a conversion factor or a fraction. Some people like to do this like railroad tracks. You've seen that in high school. This is the same thing. So each of these boxes is the fraction. The thing I want to get rid of is on the bottom. The thing I want to go to is on top. Now, on Wednesday, that was moles. Today, I want to go to milligrams. And then I have to have my conversion. In chemistry, pretty much every time we're changing something, it's by a factor of 1,000. Okay, so we might be dividing by 1,000. We might be multiplying by 1,000. Move that decimal and sets at 3. So a gram, that's about the mass of a raisin or a paper clip. A milligram is about the mass of a grain of sand. So do I have the mass of 1,000 grains of sand in one paper clip, or the mass of 1,000 paper clips in one grain of sand? The first one. So that means I'm going to put my 1,000 grains of sand, my 1,000 milligrams on top, and my 1 gram on the bottom. Okay, so when I'm multiplying by factors of 10, I'm just moving the decimal. However many zeros I have, that's how many decimal places I move. So 3 zeros, I'm going to move this 1, 2, 3, or I can plug it into my calculator. And I'm going to end up with 51.8 milligrams. Okay, I don't need to put these zeros here. Okay, we don't generally write zeros if we have something before the decimal. So these are just placeholder zeros, right? They're not significant. So if I have 3 significant figures here, how many significant figures did I have here? Also 3, because changing the scale does not change the number of significant figures, okay? So my left-hand zeros, I'm going to lose them, okay? Left hand is not significant, okay? Now I could do this again. So let's say I wanted to go to micrograms. So there are 1,000 micrograms, and micro uses the Greek letter M, which looks like a cursive U, but it's really an M. And there's 1,000 of those in 1 milligram. Okay. So if I take my 51.8 milligrams, have my conversion factor, milligrams on the bottom, because that's what I want to get rid of, micrograms on top. There are 1,000 of those. 1 grain of sand. Catch up a little bit. I multiply this out, and now I'm moving my decimal place again by 3. So I moved it 1, so I've got the 518, but then I don't have any other digits to move it past. So the way that I show that I'm moving that decimal place is I add zeros. So this confuses people sometimes because they're like, well, aren't I now showing 5 significant figures? So am I? No. So the rule for the right-hand zeros is a little more complicated. If there is a decimal point, then these are significant. If there's no decimal point, they're not significant. So again, these are placeholders. These are just showing us how big that number is, rather than telling us whether or not we know this. I don't know that 0. I don't know that 0. So the decimal point is what says, yes, I know this, or I'm not really sure. Okay. All right, so this kind of confuses people, but if you have to keep moving that decimal over and there's no number to go past, you're going to put in zeros, but make the decimal point invisible so that it's not showing that it's significant. Now we could also go in the other direction. Grams to kilograms. And again, kilo means 1,000, so we're going to move that by a factor of 1,000. So we had, what was it, 0.0518 grams. We want to get rid of grams and go to kilograms. Now where's my 1,000 going to go? On the bottom, because there are 1,000 grams, 1,000 paper clips in 1 kilogram. So 1 kilogram might be like a thick notebook or a paperback textbook. Okay. So 1,000 here, 1 here, multiplying. And so since I'm dividing by 1,000, which you can use your calculator, but since I'm dividing, I'm going to move my decimal in the other direction. So it's going to go this way. And again, I'm going to put in placeholder zeros where I don't have them. Okay. So I don't want to write that in right now, but 0.00 518. Okay. So this had 3 sig figs. How many does this have? 3. The left-hand zeros, they are important. We still need to write them, but they are not significant. So when I'm counting sig figs, I'm not counting those. So when I have a number like this, I actually prefer to have it in scientific notation because it's kind of hard to keep track of all of the zeros. So if I'm writing this one in scientific notation, it becomes 5.18 times 10 to the minus 2 grams. And this one is 5.18 times 10 to the minus 5. The first part here shows the significance. Okay, in scientific notation, we always have some number before the decimal, some non-zero. So you're just counting all of the digits that are shown, okay? If I were to write this number, I would not include those zeros. I would write 5.18 times 10 to the 4th milligrams. This part is what we mean by order of magnitude. That's how big or small the number is. So when I put over here scale or order of magnitude is like, is this number in the tens? Is it in the millions? Is it in the hundreds? This does not show significance. So when I'm looking at this number, 5.18 times 10 to the 4, the reason I don't put those zeros there is I don't want to imply that I know what those zeros are, because I don't. They might be 1s or 2s or 3s or 4s. Yeah.
Sorry, but it's significant, like in the scientific notation, you can only have like 5.2 or like only a number in the tens place, but sometimes also like 5.18 or like the numbers that keep going. So like
You can have any number as long as you know those numbers.
okay.
So like if you were to do pi, you know, people know hundreds of digits of pies. You could do, I mean, like it'd be silly because it's 3, but I mean, you could do 3 point blah, 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 blah times 10 to the 1. No, not 10 to the 1, 10 to the 0. So yeah, with scientific notation, you can have, this needs to be just one number, but you can have all of those. Now, that being said, if you were to type into your calculator, if you were to put 51.8 times 10 to the 3, your calculator is going to say, oh, that's the same thing as this, and it's going to know what to do with it. Because this is just a math problem. If I take 51.8 and multiply by 1,000, that's the number I'm going to get. But proper scientific notation will only have one number before the decimal.
Right.
But after the decimal, as long as you know them, it's fair game.
So like typically, of course, not really zeros. If it's like a non-zero digit, then you're probably fine.
Yes. All right. Now the rules are when you multiply two things, how many significant digits are you going to report?
Only small.
Yeah, so we have a product and we have our multiplicand, the things we're multiplying, right? Between all of the things we multiply, so it might be 2 and it might be 10, whichever number has the smallest number, that determines, not the smallest number, the fewest significant figures. That's how many significant figures we report. So if I multiplied a whole bunch of things that I have 10 significant digits, and then I multiplied it by 1.1, my final answer only gets 2 significant digits, okay? Adding is a little bit different. So 90% of the time in chemistry, we're multiplying. Sometimes we add, okay? If we're trying to find the formula mass, we sometimes know things like fluorine. I think this is what it was. Let me double check over here. We know a bunch of digits on fluorine. Okay, so we know a whole bunch of those. Now let's just pretend that we only know this for hydrogen. okay? So what's my rule here? If I'm adding those together to find the mass of hydrogen fluoride or hydrogen monofluoride, I'm going to cut off at the 8th. Okay, that is correct. Now, articulating why is a little bit difficult. We know these digits, but for this column, this place value, I know the 4, but I don't know what the next number is. So I can't report to a place value that I don't know, okay? So this is question mark, question mark. So I don't really know what 4 plus question mark is, right? So I'm only going to go to the place value as far to the right that I have information for everything. Let's see. 1. And I guess that carries the 1. So this is 1. Okay. So this is how I would report it. So this is why I don't say use this number of significant figures when you're adding your molar masses. I say report 2 decimal places, because everything on the periodic table, except for the radioactive ones, we know at least 2 decimal places. But some of them, we only know 2 decimal places, okay? So we could get a little more information by adding the stuff out there, but we're gonna get a lot of significant figures over on this end. Okay, so this paper basically just summarizes those things. For your test, I will mark on there when you have the significant figures wrong. I won't deduct points on this one test. In the future, I will start deducting points after you've had some feedback on doing those points. If you give me too much information, so if you wrote 4O here, then I might write -1/2. Because tacking on that tiny little bit at the end isn't really going to affect your final result a whole bunch. It's just saying to people, I know this answer more precisely than I really do. If you were to cut off information, if you were to say, oh, well, this is about 20 and leave off the 0.009, well, this implies that I only have 1 significant figure here. Then I'm going to take off a whole point. Why? Because when you leave off this information and then you use it in your next calculation is a little bit wrong. So this is called propagation of error. And so you can end up with a final result that is way off because you dropped information. And once you drop that information and start calculating with it, you can't get it back again. Okay? We can round later to get rid of this information, but we can't get back the lost information if we leave it off. So I'd rather have you give me an extra digit than cut it off too soon. Since our compounds always have the same formula, the ratio of the atoms or the moles is always the same. This means that the ratio of the masses is also always the same. So we can determine the percent of a compound that is made up of a certain element. So a percent is a part divided by the whole because it's per 100%. And so the bottom part is always going to be the whole thing that you're looking at. Okay, so some people try to divide one element by the other element. The bottom part of your percent, always the whole thing. So we're going to take whatever element it is and divide it by the formula mass of the compound. So if I have sodium chloride, sodium weighs 22.99, chlorine weighs 35.45, and together they weigh 58.44 grams per mole. So in order to find the percent sodium, I take 22.99, which is the element, divide by 58.44, which is the whole compound, and I end up with 39 points. Open. 84%.
So while the atoms are in a 1-to-1 ratio, the mass is not, because each sodium atom weighs less than each chlorine atom. So the mass of table salt is only about 40% sodium, and the rest of the mass is going to be chlorine. So I can do chlorine as well. I'm going to have my 35.45 divided by the whole, 58.44. And I always forget to do this. I forgot up here. We got to multiply by 100%. I just like automatically do that in my head, and I forget to write it out. So this ends up working out to 60.64. Okay, so in theory, if I add those 2% together, what should I get? 100%, because there's nothing else in there, right? That should be the whole. It turns out that in this case, I get 99.98%. And that's because when I do these divisions, I have to round somewhere. And so in rounding, if I round down both times, then I lose a little bit. If I round up both times, I gain a little bit. So it doesn't always work out to exactly 100. But if you're this close, you're doing fine. Okay, it's usually more helpful if we try and go in reverse. But we do need to keep in mind that if I don't have a 1-to-1 ratio, if there are more than one atom in the formula, then I need to account for that more than one atom. So let's take a look at water. Yeah, 18 or 18.02. We're going to go with that one. You already know that. The percent hydrogen in H2O is then going to be 1.01. But there are 2 hydrogen atoms, so I need to count both of those. So I'm not just going to put 1.01, I'm going to do 1.01 times 2. Okay, and so this is going to end up, times 100%. This is going to end up at about 11.2%. All right, and then if I did the oxygen, you got 16.00 over 18.02 times 100%, and this works out to 88.8%. And so we have the percents. Now, mostly we don't need to know the percent masses of things, but if I have a compound that either I don't know what it is or I think I know what it is, but I want to be sure, I can send it off for what's called elemental analysis. So I make a compound in the lab and I'm like, I think I made this, but I want to make sure. So I send it to a company and they write back and they say, this compound is 11.2% hydrogen and 88.8% oxygen. Does that fit what you think it is? So how do you figure this out? The way that you can go from the percent mass to the empirical formula is to go from mass to moles, because remember the formula is the ratio of the atoms or the moles. So we need to have masses, but we have percents. It's best to assume you have 100%, 100 grams. And the reason you do that is because it makes it really easy to figure out what mass you have of each element. So what's 11.2% of 100 grams? 11.2. So basically you're taking each of your percents and turning them into grams. Okay? Then convert from grams to moles. And then, just like we talked about before, to figure out the ratio, you're going to divide by the smallest number of moles. Okay, so let's see what this would look like for water. So we have the mass of each of them. In order to get to moles, we are going to need the formula weight or molar weight of each of these. I usually put FW or FM because if I put MM, then it's a lot of M's and that's confusing. So I'll use formula instead of molar. All right, so for hydrogen, that was 1.01. For oxygen, that was 16.00. And then I convert to the moles and I end up with 1.11 and 5.55. All right, I think it would be best if you plug this into your calculator later on and make sure you get the same numbers. What did I do to go from here to here? Multiply or divide? Divide. So if we look here, if I multiply these two, I get a really big number. So I had to have divided. So this is a division. All right. So that was step 2. And then step 3, divide by the fewest moles. So am I going to divide by 11.1 or 5.55? 5.55. Sometimes people just do the big numbers divided by the smallest. But then if you do that and then you get to the end and you're like, oh, but now I have something that's not a whole number and you get confused and on a test you're panicking and whatnot. So don't do that. Just go ahead and say 5 divided by 5. So this is going to give us 1. And this is going to give us 2. So we have 2 hydrogens and 1. I'm going to put OX so it doesn't look like 10. So I have 1 oxygen. Okay. So that means my formula is H2O. That's the formula I would expect. Yeah, because we were talking about water. Okay, so let's think about something that we don't already know the formula for. That worked out nicely, but we already knew the formula for water. So what often will happen is if a chemist is working on a compound and they're just looking at these white crystals in the jar or this blue solution or whatever, they think it's what they came up with, but to know for certain, they'll send it off for elemental analysis. So somebody will do some experiments and then say, okay, this is the percent of your sample that is made up of these particular elements. And they can go back and say, okay, is that the right percentages for what I think I made? Okay. So let's say that we were doing phosphorus acid. So phosphate was one of the ions you're supposed to memorize, but to turn that into an acid, 8 becomes what? 8 becomes ic, right? So nitrate becomes nitric, phosphate becomes phosphoric acid. So phosphorus acid actually comes from phosphite. Okay, so since you haven't memorized phosphite yet, I thought this might be a little bit more unknown. Okay, so I'm going to make a chart here. I'm actually going to put P in the middle because in the formula P is in the middle. Okay, so we know mass, molar mass. So sometimes I'll put FM or FW for formula, and that's just because if I put MM, then that's just a heck of a lot of M's and it gets confusing. And then we want to know moles for each one. And then we need to divide by something. Okay, so our mass here, what mass am I going to put for hydrogen? 3.7 up, right? So I say I have 100 grams, 3.70% of 100 grams is 3.7 up, okay? My phosphorus was 37.77. My oxygen was 58.554 grams. Okay. Hydrogen I've been working with a bit, that's 1.01. Oxygen, not too hard to remember, so I probably don't need to look that up. How am I going to figure out phosphorus? Yeah, you just look at the periodic table, okay? And I know that for many of you, that's like, well, yeah, of course. But sometimes in the heat of the moment, you're like, oh no, was I supposed to memorize this? No, that's what your periodic table was there for. All right, so somebody look at that for me. Phosphorus, what's the molar mass? 30.974. All right, now I can leave that 4 on there. We do know that number. If you just wanted to put 9.7, that's fine. In my calculations, I left the 4 off, so if you plug in 4, you'll probably get a little bit different numbers. So what I want you guys to do is these two tables, I want you all to figure out what is the number of moles of hydrogen. These two tables, I want you to figure out the moles of phosphorus, and these two tables, I want you to figure out moles of oxygen. And remember, you have a calculator on your phone, okay? And if you're trying to remember which way to divide, look at the number of grams of your element. For example, hydrogen here. Should I have more than 1 gram or 1 mole of oxygen? I should definitely have more than 1 mole, right? This is more than 1 mole. This is more than 1 mole. So when you do your division, you should end up with more than 1 mole. All right, what do you got over here for hydrogen? 3.66. I don't like grams though, because remember our grams are canceling, so moles, very good. All right, anybody in this column here, do you have phosphorus yet? 1.219, okay. 1.219, and since I have 4 digits here and 5 digits here, I can keep all 4 of those. And then over here, what did you get for oxygen? 3.65. 3.65. All right. So we are going to divide by which of these? The smallest one, the 1.219. So we are going to divide by 1.219. All right, so you're going to do the one for the same element that you did before. And so in each case, we want to know what is the ratio of that element to phosphorus. All right, so I'm going to ask my phosphorus people first, because you can do this in your head. What's this? 1. Okay, so there is 1 phosphorus for every 1 phosphorus in this formula. All right, so back table there. What did you get for 3.66 divided by 1.219? 3.002. Okay. Now, when we are trying to find the empirical formula, we want a whole number. So if my next digit is 0, then I can probably go ahead and round that to the whole number. So this is going to be 3 hydrogens. Okay, what did you guys get over here? 2.99. Okay, again, not exactly a whole number. If this number is 9, then it's probably safe to round up. Okay, so this is going to be 3 oxygens. So my formula then is H3PO3. That is phosphorus acid. Okay, we will go over other examples on Monday, and in particular, you will want to pay attention to in the reading about organic compounds, because we find what those masses are from the products of combustion. It's called combustion analysis. I want to briefly introduce balancing chemical equations. Anybody never heard of balancing chemical? There's some people haven't had a lot of chemistry. Okay. So the idea of balancing a chemical equation is that we want to have as many atoms of each element on one side of the equation as we have on the other. Okay, so Dalton's rules say those atoms can't be created or destroyed. So if I started out with 3 phosphoruses, I should end up with 3 phosphoruses. So in balancing equations, the whole idea is to get back to having the same number of each element on each side. All right. So I have a question here. Which law requires that? It's the conservation of mass, because that says we aren't created or destroyed. Okay, so first I want to look at an example so that we can kind of see why we have the rules that we have. So we're going to look at water first. Water can be made from hydrogen and oxygen. Now, is this equation balanced the way it is? No, because I seem to have lost an oxygen. So when you are balancing an equation, you are not allowed to add new chemicals. The equation as it is given to you is the equation. There's nothing else there, okay? So we can't just say, oh, let's put an O there. That's not allowed. We also can't change our subscripts. The subscripts, the bottom numbers, tell us what the molecule looks like. This molecule we know is water. Does anyone know what this molecule is? Yeah, hydrogen peroxide. So if you've seen this before, it's probably been in a brown bottle that you have in like your medicine cabinet or perhaps the laundry room. Maybe put it on cuts and it gets all fizzy and bubbly and maybe hurts a little bit. This is not the same thing as that, okay? You do not want to be drinking hydrogen peroxide because it kills germs. You know, if you drink enough of it, it might kill you. So what are you allowed to do? Oops. You are, you are allowed to change the coefficient to a whole number. Okay, so the coefficient is the big number at the beginning. So I can change those. Now coefficients can't be negative, and it can't be fractions, and they can't be zeros. So in this place where there doesn't appear to be anything, what number is implied? 1. Okay. So on Monday, we will work through how do we figure this out. Now, something like this, a lot of times people just sort of play with the numbers until it works out. But if you have a more complicated problem, then you might want a method to figure out how to sort it out. All right, have a good weekend. Festival of the Horse is this weekend. Food trucks and fun stuff going on Main Street, just a block from campus. I suggest you check it out. And what? And there's a home football game. You should go to the home football game. Absolutely. Thank you. And the color by number sheets are here if you want one.
Is there a time to come in and make it, please?
Yes, I have classes at 10 and, well, this is 10, 11, so I have one right now, and I have one at 1. When are your classes?
My next class is at 2, so I
Okay, so 2 doesn't work for you.
could probably come in at 1.
Okay, so what I'll have you do is I'll print out it. Well, do you have a laptop you can bring?
Yeah.
Okay, so just bring your laptop and I'll get you set up on the computer to do that.
All right, sounds good. Yeah.